I didn't share right now, but only you share. Oh. Right, and then you can just you know, we talk about this. What about this? But never mind you. Three. Oh, good example.
Yes, here. Okay. Okay, can everybody hear me? Nice. Okay. Hi everyone, I'm Jack from 1X. I'm excited to present on our World Model Challenge and its winner. I first want to just say a huge thank you to the Open Drive Lab team. They've put in a lot of work to make this all come together. So thank you all very much. Yeah, so a little bit about 1X. We're a humanoid robotics company. We were founded in 2015. We began engineering highly compliant gear systems and then later applied that technology to build complete robots. Currently, we're at now around 300 employees, many of which have joined in the last year. On the AI side, we're around 30 employees. And really the main function of the AI team is to enable our robots to perform tasks autonomously in households and other unstructured environments. So before I discuss the World Model Challenge itself, I want to start with an uncomfortable truth, which is that in robotics, simply adding more data or parameters or GPU hours doesn't necessarily result in better policy performance. And we see this in many works, that have kind of come out with over the past few years, which is, that leaner networks or more carefully selected data sets can actually outperform their larger counterparts. And yet we shouldn't abandon scale. History shows that, transformative capabilities can really arrive when you kind of add these, order of magnitude increases in data and in compute. We see this in LLMs and video gen, et cetera. And so robotics should not ignore this. But at the same time, if you're going to make a big investment in training a model, then you should be able to accurately predict whether that investment is going to result in a more capable system. So why don't we already have these scaling curves? And there's a few reasons you might point to, but a major issue is that measuring progress in the physical world is hard. In other fields, you can evaluate the quality of a model by running benchmarks digitally, and no matter where you are on the planet or what cluster you're running these benchmarks on, you'll get the same results. But in robotics, it's quite different. To evaluate, you have to run on a physical device in a physical space where background and environment shifts, hardware wears, camera calibration changes. And we've seen this anecdotally, where if you train a model on a given day and you have high performance on a task, then over the next few weeks, you can watch accuracy kind of slide down to mediocre performance and even bad performance. So this kind of policy decay really blurs the real effect of scale. You want to ask the question, maybe, is the larger model that you just trained really better, or did the environment just move? And so, until we establish time-locked, standardized test beds, scaling results will remain noisy and hard to trust. And that's where world models come in, which are digital twins of the real world and allow for the creation of a test bed of perfectly reproducible conditions to roll out policies. Of course, the important caveat is that to receive meaningful results, one needs a high fidelity world model capable of modeling a robot's actions and the responses of the environment to those actions. So, there's still this kind of major question and research challenge of making world models practically useful. And that's why we launched the 1X World Model Challenge with two sub-challenges called compression and sampling. So for the compression challenge, we take inspiration from NLP and vision, which have shown that optimizing a single clearly defined objective of predicting the next token can yield highly expressive models. And in robotics, the corresponding objective is to predict the logit of the next frames, or the logits. A lower cross entropy loss on a held out test set signifies that the model has distilled more of the scene's structure, including its objects, motions, and lighting. For the sampling challenge, we advanced the problem from representation learning to generation. So given several preceding frames, the model must synthesize the subsequent frame. And the prediction is assessed with PSNR here, relative to a ground truth frame. So high fidelity, coherent outputs demonstrate that the model is able to project the physical world forward and is able to really function as kind of a neural stimulator for our robots. So we're really excited to announce that Duke has placed first in both the compression and sampling challenge and is our overall winner. The team will be walking us through their work next, so I'm happy to give the stage over to them.
Yes, welcome, Duke University to extend their winner, winner members.
Models, Genie, which is a model that lets you generate interactive world models, which range for roughly 800,000 steps on one dataset. As you can see in the background, there was poor environment consistency. For GR1, and this is a world model that is built specifically for robot interactions, and the inputs it takes are sequences of observation images, robot states, and texts. But for this world model, we ultimately found that there was too many issues with input-output modalities. And then, as mentioned earlier, as undergrads, we had limited access to compute resources, and while we got okay results of the base Cosmos model, as you can see there, this model was released halfway through while we were already testing for this challenge, and the 5 billion parameter model was simply too big for us to successfully host.
So overall, these models we found a common struggle with handling variable length input and long horizon of this challenge. And this leads us to our solution, which is a framework that came out a couple months ago called the diffusion force transformer. And when we found this, we thought it was perfect for the world model task, and we want to discuss a little bit more about why. So with the diffusion force transformer, how is it different from a normal diffusion transformer? Well, it introduces something which is noise as masking and independent per frame noise levels. Now, what does this exactly mean? Well, in a normal diffusion transformer, the history is actually encoded and it's treated separately as our prediction target. But what the diffusion force transformer does is it gives a variable noise to the history and the prediction target. And that allows much more robust generation with arbitrary context. And since we're working with a very large video context, this happened to be perfect for the world model job. Another thing about this approach is it includes something called history guidance. And what this does is it solves the problem for those familiar in the diffusion space of classifier-free guidance. Because with classifier-free guidance, a lot of the times what you have is you're trying to nudge the model towards a condition, but this ends up overfitting over long horizon rollouts. And also the model learns that the most stable way to generate frames is to just replicate the very last frame. So this history guidance is really important. So the authors of that framework had a couple different backgrounds, including VAEs, the diffusion transformers, but the one we chose was Human3D. It has a unit that acts as a local feature extractor, and it includes both res blocks and transformer blocks, which is going to allow us to capture local and global context. And it happened to also be really compute friendly because it came with rates pre-trained on real estate data set. It's ended up being 500 million trainable parameters.
So after training for 750,000 steps, our model showed promising results, but was failing to basically interpret the actions correctly. So notice that instead of reaching for the table and closing the river, the model is instead doing camera motions. So camera motions that don't reflect the action numbers. So therefore, we need to essentially train the model to translate raw state vectors into correct visual movements. So if, for instance, the actuator roll pitch yaw changes, which should be reflected by arm movements, and for changes in the robot-based velocity, which should be reflected in changes in camera motion.
We started off with a naive approach just by adding the external conditions to the same dimension as the noise band. And we found that this got some improvement. For example, you can see in the videos that the arm is actually gripping and placing things, and it's also grasping at the right time, but it's just not having the exact motion that we desire. And so we decided to look further into this post-modulation problem. And what we found after review is that this modulation problem has been discussed in the diffusion and resonance many times. And so we took inspiration from papers like film and the diffusion transformer paper. And instead of adding film layers or additive with text conditioning, we replaced that text conditioning with post states. And we put that into our Ubiquity architecture in the res blocks and the transformer blocks, which is going to allow us to inject kinematics info at both the local and global levels. And you can see right away that we're achieving much better results in terms of accuracy of the actual robot arm. So the left here is our model output and the right is ground truth. And just for a little bit of extra info, you can see when our model is generating frames and not context when the frames turn green on the left. So we essentially solved the pose modulation problem, but one thing we saw was a little bit of color collapse as videos generated. And the reasoning behind this is that there might be some colors or environments that weren't as represented in the training data set as they were in the validation data set. And so the way we solved this is very straightforward, which is Gaussian blurring and space-square matching. So we're going to go through our results a bit. Here are some examples of object manipulation. You can see that the robot is able to drop the coffee cup and it kind of stays there. And also it's able to pick up blocks and remove them from the environment. So one claim of world models is that they're able to manipulate non-rigid objects better than physical simulators. And we have some examples of kind of accurate non-rigid object manipulation. So the cloth on the left, as well as t-shirt folding on the right. And then we have some examples of exhibiting environments and self-awareness. So I think there's kind of a rendered a little weird on the right, but as you can see on the left, it's aware of its own body shape, and on the right, it has to auto-generate the rest of the room. So the room looks a little different because it doesn't have that context. And then here's some just quick modes of failure, some hallucination where the model generates some random objects. On the right, you can see that the cloth is supposed to remain on the table, but kind of disappears. And then sometimes it's not given quite enough context to understand what's behind its arm. So there's an example on the bottom where it generates an extra block. And yeah, this will be for after the presentation, I guess, for when the presentation is released on the webpage. You can check out some of our full page of our results. And yeah, here are results. So we achieved pretty good results over the second and third place team. And we got a valid PSNR of 26, a test of 1.5, and our post-processing was able to achieve a pretty good PSNR group.
So now for the second part of the 1X challenge, compression, it works very similarly to the sampling challenge with the same state vectors as input, but instead of raw video, the input has been tokenized by the NVIDIA 8x8 tokenizer. The goal is to predict the next 3 linking grids, and performance is measured on a subset of the top 500 logics that are drawn from the full 64,000 entry. So our initial approach for this was to use a spatial temporal transformer due to the good results we saw with the transformer-based architecture during the sampling challenge. But as you can see from our loss curves, this ultimately didn't end up working well. The loss curves did not converge or reduce. And we hypothesized that this might simply be due to the fact that the data set is not large enough to train an entire transformer architecture from scratch. So after the transformer underperformed, we decided to experiment with some other models. We noticed that the tokenized data still looks pretty similar to images and videos, which are what historically CNNs perform well on. So after some fine tuning, the final architecture we used is shown here, 72 million parameter film conditioning residual CNN. It embeds video tokens and action bubbles. And then uniquely, I think the network's final layer directly predicts logics rather than features or embeddings. So this allows us to avoid a separate encoder, and it lets us train with a single cost entry loss the latent grids. And after training from scratch on the 840 for 70 epochs, we achieved a top 500 cost entry of 7.49, which achieved first place on the leaderboard.
Yeah, so to conclude, we have some specialized architectures that we choose for sub-problems and load models. So for the long horizon prediction problem, we took the diffusion force and transformer approach. and we pretty uniquely use the CNN for the latent compression. And I think some effective takeaways for world models is that I personally think that it's useful to use both convolution and attention layers for both the kind of local time step information as well as global. And then post conditioning can be straightforwardly implemented with the failure out approach. And for some future work, I think if we had a little bit more time and compute, I think comparative studies would definitely help with explaining why these models work really well, and then combining the compression and sampling approach. And I think in general for open problems and world models, that these are still hard to solve. And we found these as well, is this problem of object permanence, object-object interactions, as well as an evaluation framework, I guess, more robust than PSNR in the future.
So we like to thank all of these works scientists that we use as reference for our solution. And then lastly, we'd also like to thank the Open Drive Lab team and the OneX team for hosting this challenge.
We'd also like to thank our friends back into their support and their guidance. And thank you for listening to us not only talk about the approach, but how we came up with it. Thank you so much.
Yeah, thank you. Yeah, we have design certificate for you. So let's welcome OneX Technology guys to hand it to you. So yeah, congratulations on your champions. Thank you all. Yeah. Okay, very good.
Thank you so much.
Thank you. So we have next speaker, Professor David Crandall from Indiana University. So
David is a Latin professor of computer science and inaugural director of the Latin Artificial Intelligence Center at the university. And he's going to talk today